This is the 150th anniversary celebration interview with Professor Maria Zuber. And if you don't mind, I just got a hold of the Zuber report because of the announcement from the provost yesterday. So I was going to ask you about that first, and then we can go back and kind of proceed. Is that okay with you?
That's okay.
Okay. All right. So can you give me a summary of what were the recommendations in the report?
Okay, so the Zuber report was commissioned by the provost and the chancellor to consider environmental activities at MIT. And so MIT has gained a lot of notoriety recently as a leader in energy, but it seems not to be at the tip of everyone's tongue when you raise the term of the environment. And so I was asked to work with a group and to try to understand what we really have going on in terms of the environment and where it could go. And so we had representation on the group from all parts of the Institute. We had students who were fantastic. We talked to a lot of people, really, as many people as we could in the time available. And what became apparent is that there is a great deal of interest in the environment at MIT from the standpoint of engineering, science, social aspects, policy, but that it was like the let a thousand flowers grow. It was distributed all over the place, and so what we thought is that if we did nothing else other than to coalesce those activities into a handful of unifying concepts, that MIT's visibility in this area would grow, because all of the individual research efforts that we saw were really of the highest possible quality. Okay, and so we suggested some ideas in the report. We talked to students about how the environment, their access to environmental courses in the curriculum, and there wasn't a single place where you could go to try to understand what environmental courses there were. But our students are they're very savvy, and so they manage to somehow navigate their way through the system, no matter how the information is set up. But it certainly would take individuals who had some desire to go into that area to really dig. And so we suggested some concepts for future study, and we suggested that the Institute in particular looked at the idea of sustainability. And the interesting thing about sustainability in the environment is that when you talk to different people, you get lots of different definitions about what sustainability is, and no one really, like we talk to people in science and they would say sustainability, oh, that's engineering, you know. And but sustainability was something that overwhelmingly the students wanted to learn more about. So we started a dialogue about what we saw sustainability to be and where it should go. And it was interesting because the group of people that was put together on the committee came from all over the Institute, and several of them they felt a little bit unloved because of all the attention going with energy, and so I really I was a little bit concerned about whether we could really get a report together that the whole group would buy into. But actually, by the end of the process, everybody was so excited about the possibilities that existed for taking this idea forward that the entire committee asked me if they could all sign the transmittal letter to the provost and chancellor to underscore the depth of their support for moving forward on this. The provost almost fainted when he saw the letter, but it was great. And so then there's been now there's follow-on work going on now by an environmental research council, which we suggested be convened, and they're now getting into the implementation stage. And in fact, today, the day that we're filming, I spent the earlier part of the day on a campus-wide symposium on rethinking water. Okay, and water was one of the ideas that we came up with that was critical to the environment. It was extremely important. It was a unifying principle, and something that I think we have a lot of work going on already now in water, but certainly by holding a symposium and getting people's ideas on the table, already there are ideas emerging for taking this forward. So
you mentioned in your report a sort of description of programs at Michigan and Berkeley and Princeton and other places. Can you articulate what it is that MIT offers that would be kind of new and different in this area?
Well, some of these other schools. So these are all great schools, and they all have great programs, and what we were able to divine from investigating the situation is that in some cases these programs had greater visibility because they had a school of the environment, okay, or a center for the environment. So it was essentially a location and a group of people who were coalesced in the same place. And in some cases, the level of effort of what was going on was actually substantially less than what MIT was doing, but it was just the way that it was nucleated. So, so I think what MIT brings to this is that we have such depth in so many different areas. Obviously we're number one in every aspect of engineering, and in science, and our social sciences and our humanities, and the business and the economics, the political science, all of these things we have just exceptional depth in. And I think, compared to anybody else, we're strong in every area, okay? And so when we get people together, we don't lack anything that the problem needs. So this is, the study of the environment. It's a complex system, and not only is the interplay in different parts of the environment systems complex, but trying to figure out what to do about it, because it requires attitudes and behaviors of people to have to change in order to do it. So it becomes a sociology and a psychology problem, as well as a science and engineering problem. And because we're so strong in all of those areas, I think that we can really go after those problems. Another thing that I think we bring to the problem is just that there's an attitude on this campus in anything that we do that nothing is impossible. Okay, I think it's being in a school that is grounded so strongly in engineering that in engineering you have to find a solution. I mean, there isn't a problem where you don't find a solution. You have to figure out how to do something, and so rather than park a problem in the corner because you say that's too complicated to really go after, it's instead, okay, well, let's take this problem, and we can't know everything about the problem, but let's pick a part of it that we can get our arms around and make progress. And so I mean, it's great to be in a place where you can't really be scared away from something just because it's a big challenge. In fact, around here, those kinds of problems tend to attract people.
And you move on now to this Senior Energy and Environmental Board at MIT. Do you know what the nature of your work in that's going to be?
Okay, so the Senior Energy and Environmental Board is a group of people, all of whom have, I think, some administrative responsibility here at the Institute, that is going to advise the provost on the environment as initiative as it moves forward, and I think really the idea of it is to assure that there is a synergy between the energy initiative and the environment initiative. So, so when President Hockfield gave her inauguration speech, she actually mentioned energy and the environment in the speech, and so initially the energy part of it took off, and I think the environment part is now catching up. So although I have to give Ernie Moniz and Bob Armstrong credit in the energy initiative, because they actually were incorporating environmental aspects into the energy initiative from the beginning, mostly related to climate issues and climate mitigation. But as we move ahead, it's important to make sure that that the two activities are synergizing in places where it makes sense to synergize, or at least not acting totally independently. So of course there are parts of environmental studies that don't directly relate to the energy initiative, and those are interesting things to study in their own right, and they ought to be studied. But in places where it makes sense to synergize, we ought to synergize. Okay, and so an example of that would be when we talk about introducing new energy sources into the stream. You know, we can come up with all these ideas, and many ideas are being put forth. But you know, for goodness sake, you don't want to create a bigger problem than you actually have. So, so for example, if you talk about wind, you put up windmills and they change the wind stress at the surface of the Earth, and how does that affect the microclimate in an area? Okay, you know, when we talk about putting out solar panels, and of course, you know, we're talking here about doing things at a scale where they actually help energy. Okay, so if we just do things at a very small scale, so that you can charge your cell phone at home or something, that's fine, but it doesn't really help the world's energy needs. We actually have to think about scaling things up to the point where they really make an impact. So if we think about putting out lots of solar cells to collect solar energy and convert that to electricity, well, it changes the albedo of the Earth, which changes how much solar energy is absorbed, which, since they're dark, actually has the potential to heat up the Earth, and that might not be a good idea. And so it's very important when we think about these things, when we think about energy sources, that we also think about the environmental impacts. We also, you know, I think we also, you know, need to think about, you know, more broadly, green engineering. You know, when we think about engineering new parts, new devices, and we train our students in the fundamentals of engineering design. I mean, it just seemed to a lot of us that environmental consciousness ought to be a part of the design process. Now, you know, green this, green that. It's a very popular word right now that gets used, and if you can do it that's good, and there's all sorts of good reasons to do it. The question is, can you afford to do it? You know, is it feasible to do in a cost-effective way that a product can be sold, and it can be sold, you know, with a design that has the right quality that that one needs, and so it seems like there's a lot of potential to infuse that into our engineering programs. So so in this board, we'll be looking for those synergies and looking for places where we can, you know, assess ideas that are coming up and maybe pop a few back on our own as well.
You sound excited.
Well, yeah, I am, and I have to say, you know, in my office, my department head's office, I have, you know, I keep putting out magazines that I get in the grocery store about, you know, about climate change, about environmental change, about energy, and you know, I talk to my faculty. I'll go in and I'll show them, and they'll say, "Maria, you're preaching to the choir." And I says, "No, I got this at the grocery store. We're relevant. This is our moment here." You know, people tend to listen to us a lot anyway because we're from MIT, but this is a time and a place and problems that have huge societal interest, not only just to a subset of the population, but to the whole world. And you know, what a great privilege it is to be able to study these problems and to forge a path forward ourselves, but even more so to provide the training for the students that are coming through here, who are the people who are really going to be inheriting this world and are going to have to solve these problems. So, so training them in a way that they can come up with the scientific, the technical, the policy questions, but also educating people in a way that they can be informed voters, I think, also on these matters.
Well, thank you. Let me turn now to the sort of more chronological look.
Okay.
Can you tell me where you were born and where you grew up?
Okay, so I was born in Norristown, Pennsylvania. Let's see, the first few years I lived, I guess, in suburban Philadelphia, really adjacent to the campus of Ursinus College, which is a little private college in the suburbs. And then my father was a state policeman, so we moved up closer to where he and my mother had grown up, and that was in Summit Hill, Pennsylvania. And it's a little coal town in central eastern Pennsylvania. It was I think the first place, at least in eastern Pennsylvania, where anthracite coal was first discovered in the 1800s. So, so both of my grandfathers were coal miners. So.
And you were the first person in your family to go to college, I understand.
I was the first person to go to college, and in fact, you know, when I was in high school, my father thought that I should. He thought it. I mean, he was really proud that I was going to be the first person in the family to go to college, and he thought I should go to the local satellite campus for Penn State that was, you know, 15 miles away from the house, and I applied for a senatorial scholarship from school. That the state of Pennsylvania has some of these scholarships, and the senator's office called my father and said, "She shouldn't be going satellite campus of Penn State. She ought to go to the Ivy League and just have her, apply to, one of the Ivy League schools. And so I applied to the University of Pennsylvania because they had a program there for students from small towns in Pennsylvania, and I got into Penn early, and then I didn't enter that program. I didn't want to go into that small communities program because I wanted to get away from people from small. I didn't want to be hanging out with other people. The whole idea of going to a school like that that's so diverse is to just see a whole different subsection of people. So I didn't enter that program, but I went to Penn, and that was good.
I know that there's one experience from your childhood that really helped set you on the path that you were interested in, and it's around, I think, the moon landing.
Well, it's that influenced me a great deal. So, but I was that was defining. But I was hooked before then. So,
how did you get hooked?
I'm positive that it was genetically encoded into me. I mean, I knew I was reading books about space from the time I could read, and actually my mother tells stories about when they were doing the first rocket launches on TV, and I was in my playpen, that I would just be jumping up and down and pointing to, and not just the launch, but just sitting there, mission control, and I'd be jumping up and down and pointing, and so I started. I read everything in sight, and I started actually building telescopes when I was 7 or 8, and the moon landing was when I was 10. So and my parents let me stay up late to watch the first to see Neil Armstrong walk on the moon, and well, I knew that that was what I wanted to do, and I never, ever for a moment deviated from that, and I did it. I said I was going to do it, and I didn't. I mean, I didn't know what I wanted to do, but I wanted to study space. Yeah.
How, when you got to Penn, how did you determine that that combination of geology and astrophysics was the right mix?
Oh, well, it was, so I majored in astronomy and astrophysics, and it was, actually it was really, it only happened because I finished my major like a year early, and I got through all my coursework, and then I took an engineering class. I thought about, I was thinking about graduate school, and I was trying to decide between astronomy, astrophysics, engineering, and then I took geophysics because it had physics in it. I said, that's good, physics. I like physics, so I'll take geophysics. And then I realized that I had so many basic science courses that I could actually get a geology major in a year because I had taken so many courses. So, so I just picked that up the last year, and then when I applied to graduate school, I applied to astronomy departments, engineering departments, and geology departments, and then just took it from there.
And why did you pick Brown?
Let's see. That's Well, actually, when I was an undergraduate at Penn, and you have to go see some advisor, the advisor says, "Oh, you should be applying to MIT for graduate school. You're a good student. You should think about MIT." And I remember saying, "I don't want to go to any nerd school. I want to go to a nice Ivy League school with a good program, so I can go to piano recitals at lunch, and I can go to lectures on novels. I don't want to go to any school with vector heads, and of course, I'm the biggest nerd there is. I mean, I studied all the time, and but that's what I thought. So I didn't actually ever apply to MIT, and my advisor was actually my high school teacher. He wanted me to apply to MIT, and I kind of said the same thing to him. So he was very disappointed. My undergraduate advisor was disappointed, and but if things fall out, here I am.
That advisor had the last laugh.
So.
Can you talk a little bit about that experience of seeing the Voyager images of Jupiter?
Voyager. Yeah, well, I was in a bar, and they had the images going by of the Voyager flyby of Jupiter, and they were showing the pictures of it, and it was really the first time any human had seen that in that way. I mean, you could see Jupiter through a telescope, and we actually had some pioneer images of Jupiter, but what Voyager showed was just completely different. It showed the moons, and I was looking at that, and I thought to myself, you could make a killing if nobody ever knew anything before, and then you have information that no one else had, and you studied it, you could make a killing. And science has gotten very compartmentalized and very detailed, where to go make an original contribution, well, I mean, it's very common in science to apply a reductionist approach, where you go in, you look at a system, and you break it down, and so as you break it down, you keep looking at smaller and smaller parts of the system to try to characterize it, and so it seemed to me that you could really, really do things of big scope if you just looked where no one looked before, and I was interested in, my interests were very broad. I mean, I loved space. I loved to hike. I'm one of these people who, I look out the window in a car and I'm fascinated. When I'm on an airplane, I always sit in a window seat. I love to look at the sky and the ground. I mean, I just draw huge amounts of inspiration out of looking at that. And it occurred to me that if you go and you look someplace no one's ever looked, you always make a discovery. You never don't make a discovery. And so it was actually that that caused me to want to do graduate work in planetary science, as opposed to some of the other fields that I was thinking about. But then when I went to graduate school, well, I was interested in that, but I somehow deviated. I got interested in a class of fluid dynamical problems with highly nonlinear viscous fluids, and I just I wound up writing a theoretical PhD thesis that didn't have a single data point in it, and just because I just was interested in the physics of the problem. But I enjoyed it because I owned it. you know, I just found something that I liked, and I figured it out, and I enjoyed that. But then, you know, I mean, I think though, really, that I'm a natural explorer, I think, and so when I finished my graduate work, I kind of always wanted to work for NASA, and so my fiance at that time, who's my husband now, he was getting his PhD at his MBA at the Wharton School, and let's see, I think I want to say that again, so because I said he had PhD.
Go ahead.
Okay, so when I was finishing up my PhD, my fiance, who's now my husband, was finishing up his MBA at the Wharton School at Penn, and he said, "Give me 5 cities where you might get a job," and I gave him 5 cities, and he got job offers in all 5 cities, and I got all the positions I applied for too, somehow, and he said, "Oh, well, you know, you've always wanted to work for NASA, so why don't we go to Washington and you take this postdoc at the Goddard Space Flight Center," and they actually hired me because the Goddard Space Flight Center, they had a very strong Earth Sciences group, and they were interested in getting into planetary sciences, and so they hired me to come in and assist them or contribute to that, and they had just won an altimeter to go to Mars that they were a radar altimeter that they were very excited about, and but not long after I got to Goddard, the Challenger exploded, and so it set the program back. So so everything slipped, and when the mission that this radar altimeter was supposed to be on, when this slipped, the cost of the altimeter absolutely skyrocketed, and so NASA, so on this spacecraft there were a number of instruments. They just totally deselected some of the instruments and threw them off to get the cost down, and then for the altimeter they decided to hold an open competition for whoever could come in with the best cheap altimeter. So so at that time all the planets were being mapped with radars, and when I had gotten down to Goddard, it was when Reagan was president, and it was in the Star Wars era, and they were putting a lot of money into space-based laser technology, and so so it just occurred to me that well, if you're putting $2 billion a year into space-based laser technology, there's probably something useful in it. So so I got my security clearance, and I went in and with some other colleagues, all of whom were about my age, and we looked at the Star Wars laser technologies, and when you talk about classified systems, it's all power, pointing, stability, jitter, and so what you do is you just take all those specs and you dumb them down until right below the classification level, and so then they've done all the hard part, and you can, so that, you know, so when they had this contest, we proposed a laser system, and in terms of performance, we blew the radars out of the water, and so so my second year out of grad school, we won a $10 million instrument to go to Mars, and then ever since then, all the altimeters that have gone to the planets until about 2 years ago had all been lasers, and they've all been ours. So, so that was good. And so that's what really kind of got things going for us. And I really got involved in that because you know, I had been doing models, some modeling of the planets, and I got frustrated because there wasn't observations available to be able to test my theories. And so eventually you get to the point where you'll go get them yourself, you know, and that's what we did. So.
And you spent 4 or 5 years at Johns Hopkins?
Probably not quite that long.
Okay.
Yeah, so I really I enjoyed being at NASA a lot. Okay, but when you have a job in a place like NASA, or any research lab really, about the best you can ever do is spend half your time doing your research, and then you spend half your time doing what I'll call company business in a way. And so at NASA, it's monitoring contracts or, you know, things like that. And I decided I wanted to teach and work with students. So so I asked the Goddard Space Flight Center if I could spend some time at Johns Hopkins and start working with some students, and they said, okay, you can do this as long as it's on your own time and it's not part of your official duties, okay? And so I did that. I went there and spent, I taught a course for a semester and started work with some students up there. And then, you know, much as I loved NASA, I just felt like the half of my time I wanted to spend in education. I just drew so much energy out of being with students and working with students and talking about what I knew. You know, I mean, you have to realize, I spent my whole life reading books and learning about space, and it was just, and you know, with students, you could just talk about that stuff, and they sit there, they're interested in it, and you know, me, that's you know, I mean, it's not working, it's just my hobby, right? And so in fact, I tell all my students now, if you play your cards right, you'll never have to work, and so I feel like I still haven't ever really had a job. And so then Johns Hopkins offered me a faculty position there, and I decided to take it and, you know, still maintain an affiliation with NASA. But I actually gave my job talk at Johns Hopkins when I was 8 months pregnant, and they hired me anyway. So go figure. But I left 8 months pregnant. I left a permanent civil service job at NASA for an untenured faculty position at Johns Hopkins. And you know, and all these people were saying, aren't you worried about not getting tenure? And you know, and I just said, well, no, because if I don't get tenure, I'll do something else. But yeah, you know, when you have kids, you know, you still do your best work. You don't do everything that you used to do, you can't make everybody happy and fulfill every request that people have, but you do your best stuff. And I thought my best stuff would probably be fine, and it worked out okay. Yeah.
How did you wind up making the move to MIT?
So I really liked Johns Hopkins. So when I went there, I realized that being at a university was really what I wanted to do, and I liked my colleagues in the department, and they were extremely supportive, and then at Johns Hopkins, you don't get tenure there until the full professor level, and I was an untenured associate professor, so I had some time to go, which was good given that I had small kids. But MIT called and said, "Why don't you come and talk to us about a position?" And I said, "No." I said, "No, I'm good." And then I went home. I told my husband at dinner. I said, "Oh, MIT called today," and he says, "Oh, well, you should go talk to them because I've been in my job for 10 years or whatever it was, and there's." He really liked where he was also, but he was at Marriott, which is a very good financial company, and it's in fact one of the top financial companies in the Boston area. So if you leave and you want to be at a top finance place, you have to go someplace else. And I said, "Well, I don't know about this," and so MIT called me back then, and they said, "Well, you have to come and talk to us because we would bring you here with tenure, and you're not tenured, so you have to come and talk to us."
Well, that makes it more appealing.
So I said, "Well, I'll come and give a talk, but it's not an interview. I don't want to interview for this position." So I went and gave a talk, and actually, I don't even think it wasn't a really good talk by my standards, because I kind of didn't want the job, okay, and they they called me up and they said, "All right, well, we want to go out for letters and we want to make you a tenured offer," and he said, it was Tom Jordan who was the department head. He says, "And you have to do this because then Johns Hopkins would have to tenure you. So you have to do this." And so I went to talk to my department head at Johns Hopkins, and I said, "Well, MIT's talking about tenure," and he kind of patted me on the head and said, "All right, go back to the lab and just keep working, and you'll be tenured here, in several years." So I called MIT back and I said, "All right, go out for the letters," and then they went out for the letters, and then Johns Hopkins decided that they were going to go out for letters, and they went out for letters at the full professor level because that's where you get tenured there, and then MIT raised it up and offered me a full professorship, and that was really something, because it was I would say an aggressive offer, and I was afraid it wasn't going to work out at either place. But I'll tell you what, I have really never forgotten the fact that they took a risk when they hired me the way they did, and so I've thought about it at times as we've gone around, And then, you know, so a number of places, you know, then contacted me and says, "Oh, we didn't know you were available." And I said, "Well, I wasn't, you know, I wasn't." And but so it was unplanned, I guess, but it turned out nice.
With MIT, did you have some of that residual feeling that you didn't want to be with all the nerds?
Well, yes and no. Well, you know, I think I told them when I says, "Look, the only reason I'm coming here because you offered me tenure," you know, and but you know, when I took the position at Johns Hopkins, I was thinking, okay, is this what I want to do? Because you know, I don't consider myself a person who just bounces around. I mean, I don't take a job to get the next job. I take a job with the idea that I'm going to accomplish what I'm going to accomplish, and so actually it kind of went through my mind. Okay, if I wasn't going to come to Johns Hopkins, where would I like to be? And the only place that I really thought had an attraction for me was MIT, because they were ranked #1 in my field, and I just said, well, they'll never hire me, so I should just do this, and it's a great place, and I should be happy about it. So, yeah. So when I came here, then I was, you know, I had the, you know, the willies scared out of me because I was showing up as a full professor. So people think you're really something, you know, and so you know, when I came here, I just says, okay, I just want to be average, okay? I want to show up. If I can only be as good as the average professor at MIT, then I'll be extremely successful. And so that's, you know, that was probably it was probably the thing that kept me going, because you know, around this place, you know, if you say you want to be the best, you know, and then you look around, it can be dispiriting really quickly. So, you know, because so many, most, if not all, you know, everybody here was all at the top of their class, and everybody can't be at the top. So if you go in and say you want to be as good as the average person in a really good place, then it gives you, it's a much better, I think, model for success than coming into a place like this and saying you're going to be the best, and maybe you can, but you can be disappointed too.
So you had these expectations of what MIT was going to be like. Can you tell me a little bit about what you thought when you finally got here? How was it different, or how was it the same as you expected?
Oh, it was okay. So the thing that, one of the things that was surprising to me was that you know, I had been in good schools. I was at the University of Pennsylvania, I was at Brown, I was at Johns Hopkins, and all of these places have really top scholars at them. The thing that was surprising about MIT is just that the average was just so high. Okay, and so, you know, as you walk around the campus, you know, any person that you look at, undergraduate, graduate student, you know, faculty, and I guess I think about it more from the standpoint of just the students that are walking around half asleep with their hair disheveled. You know, every single one of those people is just the most remarkable success story. You know, I mean, to wind up at MIT, things have to just go remarkably right, okay? And so just the overall quality of everybody, I thought, was a surprise to me. I mean, I knew I would find very, very smart people here, but it's everyone, okay, everyone. And I mean, you got to watch. You know, you could be in line for the bank machine, and the person next to you, has, you know, just made remarkable discoveries. So that, you know, that was something that was surprising. The other thing that surprised me, and had I known it and realized it, I probably would have been at MIT long ago, is just the breadth of the interests of people here. So, you know, so the classic paradigm of the nerdy person who's at MIT, you know, there are definitely people like that, but just the talent level of the students. I mean, you know, they're athletes, and they're good athletes. You know, they're you know, really accomplished musicians and playwrights, and I mean, it's and you know, students who come to MIT, they have to be very strong in science and mathematics, but to have the other aspects of their being so highly developed, that they're so accomplished in other areas, to me was just a big surprise. And so, you know, you come here, I can still go to piano recitals and poetry readings, and it's just those things from the outside of MIT, they don't get the airplay, but that community is very strong. And so MIT, it's just how good MIT is at history and literature. It's fantastic that all of this is here.
So now, do you think that your high school advisor was right?
Boy, you hate to say that anyone in authority who has ever told you anything was right, because I know nobody that I advise, I think, ever really listens to me that carefully. But I can only say I'm happy I'm here.
So when I look at your sort of list of areas of interest, I sort of have the same feeling as what you're talking about with the students, because traditionally, you know, astronomers are the ones who kind of study space, and geologists study earth science, and you're coming with a much more interdisciplinary kind of background, it seems to me. So when you're looking at volcanoes in Iceland, or mapping the surface of Mars, or creating some scientific instruments, is there sort of a thread that unites all of these interests in your mind?
Well, I'd love to be able to tell you there was a plan, but I think what it was is that I was so interested in so many different things that I just wanted to be involved in every part of the process. Okay, I didn't want to be in charge of every part of the process, but I couldn't bear to analyze data from an instrument that I didn't understand. And so actually it started at Goddard, where when I got the chance to do this, my first laser instrument, they wouldn't let me in the clean room because I wasn't qualified to be in the clean room. So I started taking all these courses to get all my engineering certifications, and just so I could go in the clean room and shoot. You know, when they were shooting the laser, it's a lot of fun. So I took all these tests, and I got all my engineering certifications, and then I felt like I really understood things. So I really wanted to go from the point of having this idea of some aspect of science that I wanted to solve a question, to deciding what measurement had to be made and what instrumentation was required to make it, and designing not the best instrument, but one that could win a proposal, which is something very different, and then analyzing the data, and then writing the papers to talk about it. So so actually I was lucky in my career, actually, that well, unlucky and lucky. So the first instrument that I won, the spacecraft was lost 3 days before it got to Mars. And in the interim, I had written a proposal for this Department of Defense mission where they wanted to test Star Wars sensors, and they couldn't test them in Earth orbit because of a treaty. So they decided to send the spacecraft to the moon, and I wrote a proposal to be on the science team, and they had a laser instrument on it. And so, people said, what do you want to be on this crummy Department of Defense mission for when you got this fantastic instrument going to Mars? And I just went, because it's going to the moon, I mean, you don't know. So then the spacecraft with the Mars instrument got lost, and so we had this moon mission, and as soon as they got the first photon back from the moon to the spacecraft, the defense objective was finished, and the mission was it was called Clementine. It was being run by the Ballistic Missile Defense Organization, and so the leader of the mission, his name was Colonel Pedro Rustan, and he escaped from Cuba, swam across Guantanamo Bay to a U.S. ship, defected, got a PhD in lightning, and joined the Air Force. And he decided he wanted to map the whole moon. And so after for the instrument that I was working on, the laser system, as soon as he got the photons back, he came up to me and he says, "Okay, this is your instrument. Come with me. Here's the computer where you send commands. You can you program?" And I says, "A little." And he says, "Okay, you can program this instrument to do whatever you want, but just don't deal with any of these other files because you might crash the spacecraft into the moon or something." So I had, was given this instrument to work with, and it had to be programmed significantly to operate scientifically, and so I learned how to do all this stuff just on the fly, really, and it was great because then I really did understand the whole process, and that was very important to me. So, and I feel like I've written better papers because I've understood the data, but I've also felt like it's really helped me design other instruments. I always say when you're going into a proposal competition, I always like to count up how many miracles do you need. So how many big technological hurdles do you have to get over, and so you figure out how many there are, how many there can be to get selected, and then you make sure you only have that many or less. And so by being a little bit broad, I think it's helped, actually.
So despite the fact that you left NASA, you have continued to do work there over the years. Can you talk a little bit about the projects that you've worked on?
Well, my unlike many research programs of professors at universities, most of the research that I do is with big teams of people. So I really depend very heavily on the contributions of of a whole lot of people. So I'm probably most recognized for the instrument investigations. So the first one that actually came to pass was the Clementine mission, which we did the first global topography map of the moon, and did a very good gravity model of the near side and a not so good gravity model of the far side, because because we never see the far side of the moon from Earth. You actually have to be in view of Earth to measure gravity at a planet. So so you can make some inferences about what's going on in the back from the way the spacecraft gets bounced around on the front, and so we were able to make use of that. But we did the first map of the crustal thickness of the moon that was global in extent, and which gave some idea of how much of the moon had melted early in its history, and that's actually, it was that work that that MIT hired me for. So then at Mars, well, that was the second time's the charm. So we sent an altimeter to Mars to measure the topography of that planet, and that was an instrument that we designed ourselves. So the first one was lost, and then well, we wanted to try to get it back, and of course space missions they're very expensive, and when you want to do a space mission, there's a lot more to it than just writing a proposal. So so actually, when the mission was lost, I actually spent a lot of time down on Capitol Hill trying to get funding put back in the budget to refly that mission, which then happened. So so we did that. So we measured the topography of Mars better than we know the topography of Earth. So that was a nice thing, and we also measured the gravity of the planet very well, and Mars rotates nicely, so you can see the whole thing. So we measured the full planetary gravity field, and so did initial models of the interior structure of Mars. We measured the topography so accurately that on Mars, well, Mars has an atmosphere, has a carbon dioxide atmosphere, and its orbit is more elliptical than Earth's orbit is, and it's tilted on its axis about the same amount as Earth. So it actually goes through seasons like the Earth goes through, and because the atmosphere is very thin, the seasons are actually more dramatic in terms of how they change on the planet. So so it actually snows dry ice on Mars in the winter hemisphere, and we were able to measure how deep the snow got from orbit, and with a satellite before that measurement was made on Earth. So we published that paper in Science before the same measurement was made on Earth. I was pretty excited about that, and actually I thought the Earth science community that we were going to get a lot of pushback from them, and that I was going to be afraid to talk in front of my Earth science colleagues about this sort of stuff. But actually, they just says, "Oh no, this is great. We got to play this up because this is embarrassing. You're over making all these measurements at Mars, and we can't, you know, and it was more of, it wasn't that you couldn't do it on Earth, it was just that the funding was available to go do these missions on Mars, and it wasn't. For the Earth, there was, when you make certain measurements for Earth, there's political things involved with it. So, I says, well, maybe I'll do Earth someday. But I deviated from that. I got won an altimeter on an asteroid mission. So, it was called the Near-Earth Asteroid Rendezvous mission, which was 433 Eros, which is one largest near-Earth asteroids, and the spacecraft orbited there. So, keeping a spacecraft in orbit around a big potato, 30 kilometers wide, is a very challenging thing, actually, and that was fun, because that was a hard project to figure out how to keep a spacecraft in orbit. So we measured the shape of the asteroid and also measured the gravity field. So we were able to get at the what the interior of the asteroid was like and how much it was broken apart. So that was the first real study like that had been done of an asteroid.
And you discovered your own asteroid?
I didn't discover it. It was discovered for me. So if you discover, people who discover asteroids get to name them after whoever they want. So I am extremely honored. My asteroid was discovered by Gene and Carolyn Shoemaker, who also discovered the comets that hit Jupiter. So comet Shoemaker-Levy, that all the pieces broke up and it hit Jupiter. So Gene was the father of planetary geology. He was the world's expert on impact basins on the Earth. He did all the initial mapping of lunar craters on the Moon. He trained the Apollo astronauts, and he had been on the Clementine mission, where I came on as like the junior, sub-junior person. They always pick a couple of junior people to come on and do all the work. In recognition of the work that I did in terms of making discoveries at the Moon, Gene and Carolyn, I talked to Carolyn told me about this because the asteroid was approved with my name after Gene had died, and she says, well, we were waiting for the perfect asteroid, and so my asteroid is a Mars crosser. It crosses the orbit of Mars, and they picked that one for me because it might hit Mars someday and make a crater. Not in our lifetimes, of course, but so to have Gene Shoemaker name an asteroid after me, that was actually one of the biggest honors that I think I've had, because I have a great deal of professional respect for Gene, and for him to have thought that I had done some good work was really meant a lot to me. So that's about what I've done from asteroids so far. We're sending a mission to Mercury called Messenger, and we haven't been to Mercury for decades, and Mercury's not that far away, actually. And the reason is it's close to the sun, so it's, first of all, it's hot and it's hard to get into orbit. So, the Messenger mission was launched, and it takes a long time to get to Mercury, because what has to happen, if you think about the sun, if you're launching a spacecraft, the way you get into orbit around a planet is you fly near it, and then you slow down the spacecraft enough so that the planet's gravity field captures it. Okay, so so the problem with going to Mercury is because it's close to the sun. As you come in and go close to the sun, you speed up. So it's a little bit like a penny in a wishing well. As it spirals in, it speeds up. And so when you send a spacecraft to Mercury, it has to be almost all fuel. And then you can still barely get into orbit. And so what you have to do to get into orbit is fly by everything, to use planetary gravity assist to slow you down. So the spacecraft flew by Mercury 3 times and flew by Venus twice. And every time it flew by, it did it in a way that it would slow the spacecraft down. So we actually have gotten data from 3 flybys of Mercury, and I'm pleased to say we've written several really substantial papers with Mercury, and we had only actually imaged 40% of the surface of Mercury, so even flyby information caused us to learn a lot. But because we've learned that the crust on one side of Mercury is substantially thicker than the crust on the other side, and that's a pretty good discovery for having not even gotten into orbit yet. So so next year we get into orbit, and there will be a lot more to come in that regard, I think. So, but Mercury, that was the hardest instrument we've ever designed, and the reason for that is because Mercury's so close to the sun, you just fry. It's hot. Electronics don't like to be hot, and so with the spacecraft, there's a sunscreen on it that's made of like the same material that firefighters wear. So that keeps the sun off. But where you burn is that the sun shines on the surface of Mercury, so it's the infrared radiation coming off of Mercury. And so the spacecraft is in a big elliptical orbit, and when it comes into Mercury, everything heats way up, and then it goes back out into the far part of the orbit from Mercury, and then it just radiates to space and it gets cold. So over the course of the mission, you go through all these temperature swings, and you need really, really good engineering to prevent like leads on resistors from breaking due to thermal stresses. That was a really hard, and the mirrors distort, so we didn't use a mirror. So I enjoyed that because that was a tough problem, and so a lot of planetary missions unfortunately don't get where they're going because they get lost for because it's hard, and so I guess I'm fortunate because I get as much satisfaction from the process of designing an experiment and building it and flying it and making observations on how it's behaving, and like what we call the housekeeping data, how it's performing, as I do from doing the science, and that's probably a good thing. So so actually when I went to Congress and was talking to them about reflying the mission to Mars, I said, you know, when you buy a mission to Mars, you're not buying a pile of parts. You know, you're buying people that you teach how to do something extremely hard to do, and so that's a big part of what we have to do in the group to be able to do our science, is just the process of going through all these technical steps to get to the point where we can do the science. You know, once I start getting data, the papers almost write themselves, I think. And right now, let's see, I've got a couple going on right now. So aside from Mercury, the Mars Reconnaissance Orbiter, I'm leading the gravity field team there, and we were able to measure the mass of the south polar cap of Mars, which turned out to be, that was interesting, it turned out to be the largest volume of surface water in the solar system, water ice, largest reservoir outside of Earth. So that was a nice little discovery that came out of that mission. And now we're mapping the moon topographically, and there we'll make a topographic map. It's already better than the Mars map that we had made, so this is the second planet that we've now measured better than Earth, and we're writing papers on that. So so those will be big discoveries. And then we have a mission that's going to an asteroid, two asteroids, Vesta and Ceres in the asteroid belt. So there's more to come, I think, even.
And you're one of the first women to head a major space exploration. And I wonder if you'd talk a little bit about what it's like being a woman in this field.
Sure. Well, so, you know, I have to say that it's usually not a problem because, well, I'm oblivious to everything. And in fact, when I was the first mission, I was on the Mars Global Surveyor mission, and I got a phone call from a reporter, and the reporter said, "There's 87 investigators on this mission, and you're the only woman." And I said, "No way." and so after I hung up, I went and I looked at the list, and I went, "Oh my God, I'm the only woman." And I was like, well, that must be why I get asked to give all these talks. and
win some awards.
So yeah, so I didn't, I hadn't actually noticed, okay, but I do say that, you know, earlier in my career, I overtly published with my initials, okay, because I said if I publish papers and it says Maria, no one's going to read the paper, right? So, and then some of my male colleagues were saying, okay, Maria, you know, this is the wrong attitude. You got to celebrate this, not hide it. People are going to read your papers because you wrote them. Now that you don't have to worry about that. And so I eventually switched over, and I use my full name now. But I remember the first time I ever gave a talk in the Soviet Union. So I went to the Soviet Union to a workshop there, a symposium, and I was up on the stage and I was giving this talk, and can you tell when people are staring at you? You know, it was like, oh my God, is my slip showing, or what's going on? And I gave my talk, and I just had this feeling like people were staring through me, and I finished, and then the coffee break occurred, and all these people coming up to me and says, "You're a woman." We've been reading your papers for years, and we didn't realize you were a woman. And so I went, oh, okay. So I would say most of the time it really doesn't matter too much, but there certainly have been cases where you don't get the benefit of the doubt. You know, I mean, I've been in conversations, like at conferences, where I'd be talking to somebody, and I could tell this person's blowing me off, you know, and then he notices my badge and the name, and then the conversation changes somewhat. But you know, I think it's important to get out and demonstrate that anybody can do this. I mean, you know, the nice thing about science really is it doesn't matter how you dress or what you look like. Ultimately, it matters if you do good work, and so you know, ultimately, if you can get over the hump where you know, people will read your work and take it seriously on the basis of the fact that it's good work. So,
and you have become quite a role model for women in science. Is that something that's important to you?
Well, it didn't start out that way. You know, in fact, for years and years and years, I would never be on any committee having to do with women. I wouldn't do women's mentoring. You know, I've said, don't put me on a committee, you know, a women's whatever committee, because I felt like the best way to promote women in science was to be a good scientist, okay? Not to talk about it. But I came around on that question when I became department head at MIT. I guess they had done a survey in the department of, with our women students, of how many of you would like to become a professor at a place like MIT, okay? And I mean, we had many tens of women graduate students in the department, and only one said that she would like to be a professor at a place like MIT. And she's now a professor at Yale, so that worked out great. So I invited the women graduate students for dinner. We had a dinner, and you know, I let them have it. I'm like, what do you mean you don't want to be a professor? You know, get with, you know, how could you not want the kind of life that I have? Look, I you know, I write papers, I go to conferences, you know, I travel around the world, you know, I have a wonderful husband, I have 2 beautiful children. Tell me what's wrong with this life, that you don't want this life like this. You know, we have to solve this education problem for women, and it really got me energized on this topic, and I'm pretty thoughtful before I go in and do something, because there's only so many things you can do, and I use most of the hours in a day, so there aren't a lot of leftover hours. So when I go about doing something, I want to work on something where I can make an impact, and I decided that this question of women in science, technology, mathematics was an area where I could really make some headway. So I actually now devote a fair amount of my time to this topic. So I lecture about it, I talk about it, and virtually every time I go anywhere for a visit, I always ask to talk to students, but in particular women students, and now I'm getting more interested in minority students because that's such a big problem, and it's difficult to make headway on. But I'm devoting a fair amount of energy to it because I think we can make some headway in this problem.
So much of what you've done has had sort of a public service aspect to it, and I wonder if doing research that's in the public interest is something that's overtly important to you, or is it sort of a byproduct of what are your natural interests anyway?
Well, part of it is that I'm just so excited about what I do that I can't imagine that everybody else wouldn't be at least somewhat excited by it. Maybe not quite as much as me, but I consider what I do for my research to be a great privilege. Okay, you know, I mean, I use taxpayer money for the most part to explore the solar system. And I believe that the people who foot the bill deserve to know what's going on, and I have a personal goal that I want to reach people in way who have never been reached before on this topic, and I want the textbooks to be fixed. So when a student opens an astronomy textbook, it talks about what's really out there and without the uncertainty. And I consider this to be an essential part of what I do. So.
Is that part of the reason you're such a supporter of continued space exploration?
I think that's a part of the reason. Another part of the reason that I'm a supporter of continued space exploration is that I understand the inspiration factor both for kids and for society. Okay, I was on the presidential commission that studied the Moon-Mars initiative, and part of what we had to do was just go around the country and talk to people, and I can't even begin to tell you how many people I talked to who decided to become scientists or engineers because of the Apollo landings on the moon. And these are not people who became space scientists. They became biologists or telecom engineers or something like that. But they did it initially because they were interested in space. And I also think that for society in general, we have to be pushing at the frontiers of knowledge all the time, or else we're not going to progress as a society. And I think space exploration is one way of doing that. I think there are other ways of doing that as well, and I support those activities also.
So you're involved now in some administrative aspects of MIT, and you've now been here for 20 years.
15.
15?
15.
Okay.
Yeah.
What is it that keeps you at MIT? How does MIT help or hinder your work?
Okay, I have to get some clarity on the question here,
Okay.
because what is it that
I'm
keeps
trying
me
to
in administration at MIT, or at MIT just in general?
Well, let's talk just at MIT. What is it about MIT that makes it a good fit for you?
Okay, so what is it that makes MIT a good fit for me? Well, part of it is that that the place is it's extremely interdisciplinary, and so I can be a scientist and I can do my science, but I'm also interested in developing technology to do science, and in a lot of places that stuff doesn't count. The science part counts. But I think one of the reasons MIT was interested in me, because there was the other part. And in this place where we are, I think it's easier to work between disciplines than anywhere else I know. And if you have a good idea here, it's very easy to get people interested in it, as long as it's really hard, and it's worthwhile doing. And the fact that it's just possible to create something that didn't exist before. There aren't institutional barriers to going off in very, very new directions. In fact, it's encouraged and celebrated. So I think that's what the real attraction is.
That does seem to be a consistent theme with people, that MIT is much more open than many other fine institutions of higher learning.
Yeah, it's interesting that there aren't. I don't really have problems with turf battles here, because great problems attract people from a lot of directions, and you know, as long as you bring something to the problem, it's okay. You know, it's there's plenty of credit to go along with it, and so there just haven't been any impediments to going off in new directions and doing new things.
Do you enjoy being a department head?
Do I enjoy being a department head? It depends what day you ask that question.
Are there things that you're able to do as a department head that you couldn't do otherwise?
Okay. So in the work that any given individual does, there's the work that you do, and there are things that you can enable and help happen. So for example, you know, one of my personal career goals is to develop young scientists. So when I work with young scientists and they go out and they become successful scientists, I personally get a great deal of satisfaction out of that, and I feel like education really occurs at all levels. It doesn't occur just at the professor teaches student, but I also think that developing the careers of say graduate students, postdoctoral fellows, and junior faculty are also things that that are very important for the education system and for the fields, and so as a department head, I can contribute towards the developing of those careers, not necessarily by something that I do myself, but just, you know, helping arrange a situation that puts a person in a place where they're able to move and succeed on their own. And so I take a great deal of satisfaction out of that, and that goes down to you know, even developing curricula in the department for instruction and who we accept and we don't accept. I mean, there are just all those things that that go into planning, and then also even in areas where we hire. So if I say we're going to hire in this field, and of course I execute the wishes of the faculty. So everything is very grassroots. So all of us at a faculty, we decide what we want to do, and then I go and figure out how to do it. And it's very interesting. So when, for example, when we go in and we say we're going to hire in this field, then you're going to see other schools hiring in these fields. And when we go out of a field, you wouldn't believe the complaints I hear from people in that field. So there's really the ability to really influence the direction of science in a different way, other than the individual papers that you write, and that's something that I derive satisfaction from.
What do you think are the most important strengths of your department?
The strengths of my department. I think the greatest strength is just the intellectual power of my colleagues and our students. Okay, that's number one. But I think that the interdisciplinary and collaborative nature of the department. So my department covers topics which range from the depths of the earth to the surface of the earth, mountain building processes, floods, the oceans, the atmosphere, outer space, and even other solar systems. And so we just cover a huge amount of intellectual ground. And we form interesting collaborations. And actually, I think because of the fact that we're so broad, you know, we're not all tripping over each other trying to sequence the same gene or something. We're extremely broad, and so it has a tendency to bring people together when problems arise. That we do these broad collaborations. So we've really been doing interdisciplinary science for much longer than it's been fashionable to do that in science, and the fact that we proceed and because our everybody in our department is so quantitatively strong in basic sciences in compared to some earth sciences where people are more qualitative. We can bring together many aspects of the problem, from the physics, the biology, the geology, you know, everything.
Is that part of what makes MIT unique, or maybe I should just ask you, what do you think makes MIT unique?
Oh, what makes MIT unique? Well, I think it's the thought that nothing's impossible here. That not only is it possible to address the most difficult questions, but that we're responsible for doing it. This idea of, on which the basis of MIT was founded, of service to the nation, that that those who are in a position to help ought to help, really drives us to problem solving of, the most difficult problems. And when you're solving problems that are that difficult, you need to get help. So we naturally go to gravitate to bring people together to address those things. And I think I think it's just remarkable, the esprit de corps, when the president goes around and talks to a lot of people, and a lot of people say energy, and then the president says energy, and everybody forges after energy. It's a beautiful thing, and it's so great to be a part of it, where the pace of progress is as fast as it is. I mean, this place it's always running on fast forward, and you leave and you go anywhere else, and it's almost like it's running in slow motion, and then you come back and you realize that the environment that you're in, and this seems normal, until you go someplace else.
It does, to me, it has a completely different feel than other schools that I've been involved in a similar way.
It's a cool place.
Yes. I haven't asked, all of the questions here, but it's just about 5 o'clock. Mm-hmm. So what I'd like to know is, what things have we not talked about that you think are important to talk about?
Oh, well, we haven't talked about Grail.
So let's talk about Grail.
We probably should have talked about Grail. So, okay, so I'm the principal investigator of a mission called Grail, which stands for Gravity Recovery and Interior Laboratory, and we're going to be sending 2 spacecraft to the moon, and they're going to enter into lunar orbit. And the spacecraft aren't that big; they're about the size of a dishwasher. Okay, and they're going to send radio signals to each other, and we're going to measure how the 2 spacecraft move towards and away from each other because of the way that they're perturbed by the gravity field of the moon. So I tell people we're essentially measuring the distance between 2 points, and so you can be at the cutting edge for measuring the distance between 2 points, but it's the fact that you can do it to a couple of microns when it's in lunar orbit that actually makes it rocket science. And the opportunity arose to do this, to propose a mission, and when you propose them, it's a big deal, and it's a lot of people. It's more than 100 people working on the mission, and when you do that. So it's first of all, do you want to do something like this? Do you want to write a proposal that's going to take you 6 months to write? Do you want to drop everything and write a proposal for 6 months, and then if you win, you get to spend 6 months writing another proposal? So actually doing the gravity field of the moon, I have this mental list of things that I'd like to do in my career, and this had been one of the things that had been on the list, but technologically, politically, the time is never right, but I'd actually been thinking about it for a long time. So, so when the Chinese decided they were going to go to the moon and they were going to launch 2 people into orbit, I said, it's time. It's time. We're going to do this now. And the key to winning a proposal like this is getting the right team together and getting things to click. That's, you know, there's lots of smart people out there, you know, but the difference between winning and losing is getting the right group of people together and getting a chemistry together so that you figure out how to write the correct proposal that needs to be written. And so I've been all these people that I've been working with all through my career, you know, I just started calling people, and everybody was excited. So so we got a great group of people together. And you know, since you work all the time, you like to be around people that you can get along with, because this is all about managing resources, managing risk, which means managing resources. And so we got the right people together, and actually what excites me about the mission is how thrilled the engineers are about the science that's going on, and how interested the scientists are about how the engineering is being done. And you know, the engineers that I have, they will do anything to do a little bit better in the measurement. And I sometimes have to hold them back so that we stay within our budget. But we also have, I also said that if I ever got the opportunity to do this, that I was really going to take the outreach and education part to an entirely new level that's never been done before. So when I won, I called Sally Ride, America's first woman in space, and Sally and I had been working together for years. Sally devotes her career to education with an emphasis on girls in science and technology and math. And I asked her to run the education program. And so what we came up with is that this is going to be the first mission that has cameras on the spacecraft that have no scientific purpose. The cameras are entirely for outreach and education. And they're going to be programmed by students, and it's going to be targeted at middle schools. And so middle school students will get to propose where on the moon we're going to take pictures, and there's never going to be conflicts with scientific observations because there are no scientific observations from it. So the scientific observation is just the 2 spacecraft sending radio signals to each other, which they do constantly. And so the images can just be a complete student experiment. It's the first time it's ever been done. And I'm convinced the only way I was able to do it because I had Sally on the mission. Otherwise, I doubt that would have flown in the review process. But of course, we wrote a really careful proposal. But having Sally's creative intensity and vision on this, you know, we sat down and we said, well, let's try, you know, and so I'm thrilled about the opportunity. And you know, I was initially told by a lot of people that you can't possibly win this proposal because no one understands gravity, so it'll never get through review. And I said, well, just watch. So it was the highest rated science proposal in the group of 30 proposals that they received for missions. And And we're not there yet. I mean, there's still a whole lot that can go wrong. But today, knock on wood, we're on track. You know, we're within our budget, and we're within our schedule, and and it's MIT's first space mission, so which the pressure's on. I hope I don't mess it up, but I have the right group of people working with me, and we've involved a lot of junior scientists on the team so that they can get experience, and that's something that I'm also really excited about, so that those people will then be able to go on and write their own proposals to do things like this in the future.
And of course, I have to ask, what else is on your list of things you want to do?
What else is on my list? Well, I'm actually now spending a little bit of time thinking about the outer solar system. And there I have the opposite problem of Mercury. Mercury is very hot, and the outer solar system is very cold. So I'm thinking about that. I'm also giving a fair amount of thought to optical communications, so to sending data with lasers as opposed to radio systems, and in fact we've done several technology demonstrations. So the group that I work with, we hold the record for the longest distance a laser beam's ever been fired, and then one way and two ways. So working on communicating optically, which is an important technological thing, is something I'm also thinking about. And I'm thinking about weather on other planets, and ways that I can measure that, and very precisely. So I've got a few things in mind.
A few things left to do?
Yeah.